3 months ago, during a presentation that most news outlets summarized in a single paragraph and moved on from, Elon Musk said something that, if you were paying close attention, fundamentally changed the timeline of human history. Not the history that's coming. The history that's already being written, right now. While most people were focused on the stock price, the crowd reactions, the memes, a small group of aerospace engineers and planetary scientists watching that same broadcast went very, very quiet. Because they understood what had just been said and what it meant. That's what we're going to unpack today. All of it. Not the headlines, not the press release version, the actual thing. And by the time we're done, I think you're going to look at that red dot in the night sky very differently than you did before you clicked on this. So, let's start at the beginning. Not Musk's beginning, humanity's beginning, with Mars. People have been talking about going to Mars since before the first moon landing, since before we had computers powerful enough to calculate the trajectory, since before we fully understood what the Martian surface even looked like up close, and so you'd be forgiven, completely forgiven, for hearing another Mars headline and tuning out. We've been promised Mars before. We were promised it in the 1980s. We were promised it in the early 2000s. Every decade, a new wave of enthusiasm, a new set of renders showing red dust and silver habitats, and then silence, budget cuts, political will drying up, the next crisis pulling everyone's attention back to Earth. But here's what's different now, and this is genuinely important to understand before anything else. What's happening in 2025 and into 2026 is not a continuation of those previous promises. It is categorically, structurally, technologically different. The gap between what we could do then and what we can do now isn't incremental. It's generational. And the announcement we're here to discuss didn't come out of nowhere. It came out of a decade of groundwork that most people never followed closely enough to appreciate. Think about where we were in 2015. SpaceX had successfully landed an orbital rocket booster, which was, at the time, considered borderline impossible by a significant portion of the aerospace community. People laughed at that goal before it happened, openly, on record. And then it happened. And then it happened again, and again. And now it's so routine that it barely makes the news. That's the pace of change we're dealing with. And Mars, the dream, the destination, the obsession, has been the target the entire time. Buried inside the technical briefing, past the glossy renders, past the crowd reactions, past the moments designed for the highlight reel, were 3 specific data points that left aerospace engineers quietly stunned. Not because they were impossible, because they were credible, disturbingly, excitingly credible. The first was a fuel production figure. SpaceX's team presented updated projections for in situ resource utilization. ISRU, they call it, which is the technical term for the idea of making fuel on Mars rather than hauling it all from Earth. The numbers they showed, for methane and liquid oxygen production using the Sabatier process and Martian atmospheric CO2, were not theoretical anymore. They were based on scaled hardware tests, real equipment, real outputs, and the efficiency figures had improved by a margin that, frankly, nobody outside of SpaceX saw coming. The second data point was timeline compression. Not the kind of timeline compression you get when someone moves a goalpost and calls it progress. The kind that comes from a cascade of successful tests collapsing what used to be sequential development phases into overlapping ones. What was a 10-year roadmap in 2022 had, by the time of this presentation, become a 6 to 7-year roadmap, with the first crewed Mars surface mission now carrying a genuine, engineering-justified target window that most serious observers are no longer dismissing. And the third, the one that really landed in a strange way for people watching closely, was a number related to crew survival probability modeling. Not a scary number, a good one, a significantly better than expected one. Because here's the thing, getting to Mars has never been the hardest problem. Keeping people alive once they get there, that's the hardest problem. And that number moved in a direction nobody quite expected it to move yet. We'll come back to that. Because to understand why it moved, you need to understand what we've learned about Mars itself in just the last 5 years. And that story is remarkable. Here's something that almost never makes the headlines, and it should. Our scientific understanding of Mars has undergone a near total transformation between 2020 and 2025. Not a refinement, a transformation. The planet we thought we knew, cold, dead, geologically inert, a frozen memory of something that used to be alive. That picture has been systematically dismantled by a wave of new data from orbiters, landers, and rovers that we've had operating simultaneously on and around Mars for years now. Perseverance alone has rewritten chapters of Martian geology, the organic molecule detections in the Jezero crater sediment samples. And I want to be careful here, because organic molecules are not life. They're the chemical building blocks that can exist with or without life. But those detections, combined with the mineralogical evidence of ancient lake and river systems, have pushed the scientific consensus toward a Mars that was not just wet once, but wet for long enough, and warm enough, and chemically rich enough that the question of whether life ever existed there is now taken with full scientific seriousness. Not fringe seriousness, mainstream, peer-reviewed, journal-published seriousness. Dr. James Whatley, a planetary geochemist at Caltech who has spent the last decade analyzing Mars surface data, put it this way in a 2024 paper published in Nature Planetary Science. We are no longer asking whether Mars had the conditions for life. We are asking how long those conditions persisted and whether the signatures of that life, if it existed, survived the planet's transformation. That's a seismic shift in framing. That's the scientific community moving from maybe to let's go find out. And that shift matters enormously for what humans will actually be doing on Mars when they get there. Because the mission isn't just planting a flag anymore. It never really was. But now, with the data we have, the scientific imperative behind a crewed Mars mission has sharpened into something specific, something urgent. We have sample caches waiting. We have sites identified. We have questions that only a human geologist standing on the surface, holding a rock, can answer with the speed and nuance the science requires. In 2024, ESA's Mars-IS radar instrument, cross-referenced with NASA's MAVEN atmospheric studies and data from China's Tianwen-1 orbiter, confirmed something that researchers had theorized for decades but never had the hard evidence to prove. And this is the part where I need you to really pay attention, because this finding directly influences the survival probability number I mentioned earlier. Beneath the Martian South Polar ice cap, at a depth of roughly 1.5 kilometers, Mars has detected what the data strongly suggests are multiple subglacial liquid water bodies. Not ice, not permafrost, liquid, water. Kept in a liquid state most likely by a combination of perchlorate lauret salts lowering the freezing point and possible residual geothermal heat from below. Now, the scientific debate around this is real, and legitimate researchers have challenged the interpretation. Some argue the radar reflections could be explained by clay-rich basal layers rather than liquid water. That debate is ongoing and important. But here's why it matters, regardless of which interpretation wins. The fact that Mars may harbor liquid water reservoirs beneath its surface fundamentally changes the long-term habitability calculus for human settlers. Because water means everything. Water means drinking. Water means agriculture. Water means, through electrolysis, breathable oxygen and rocket propellant. Water is the single most critical resource a Mars colony needs, and the idea that it might exist in substantial quantities beneath the surface, accessible, in theory, through drilling, is the kind of discovery that engineers and mission planners don't overlook. Musk's team hasn't overlooked it. The landing site selection criteria that SpaceX has been quietly refining over the past 2 years takes subsurface water potential into direct consideration. That's not speculation. That's in the engineering documentation. And when you see it there, written plainly, the whole project snaps into a slightly different focus. Dr. Priya Nair is a human factors psychologist at the European Space Agency. She spent the last 6 years studying long-duration isolation missions, Antarctic winter overcruise, submarine deployments, closed-loop habitat simulations. And she told an interviewer something, back in early 2025, that stopped me cold when I came across it. She said, "The psychological profile we originally modeled for a Mars transit crew was based on the assumption that communication with Earth would function as an anchor. A daily touchstone, something that kept people tethered to home, to normalcy, to a sense of continuity. What our simulation data is telling us, increasingly clearly, is that we had that completely backwards. The communication delay, up to 24 minutes one way, doesn't function as an inconvenience. It functions as a severance. And crews that thrive in long-duration isolation are not the ones who find ways to maintain connection to Earth. They're the ones who build a complete psychological world within the mission itself." Sit with that for a second, because what she's describing, and what the research behind it suggests, is that the first humans to live on Mars will not think of themselves as Earth people on a temporary assignment. They will, by psychological necessity, become something new, a community defined by where they are, not where they came from. And the implications of that, cultural, political, legal, philosophical, stretch far beyond anything the mission planners are publicly discussing. Now, I want to come back to something. Remember that survival probability number I mentioned earlier, the one that moved in an unexpected direction? Part of the reason it moved is exactly this, not the hardware, not the fuel, the humans. The growing body of research into crew cohesion, psychological resilience, and autonomous decision-making. Research conducted by people like Dr. Nair and by teams at NASA's Human Research Program and at the Moscow Institute for Biomedical Problems has produced selection and training frameworks that are, by the data, dramatically more effective than what existed even 5 years ago. The human problem on Mars is still a hard problem, but it is, right now, a less hard problem than it was. And that matters. The single biggest reason previous Mars timelines collapsed, quietly, without much public acknowledgement, was propulsion. Specifically, the gap between what chemical rockets could realistically deliver to Mars and what a sustainable human presence there actually requires in terms of mass per mission. If you've ever tried to understand the Tsiolkovsky rocket equation, the fundamental mathematical relationship between fuel, mass, and velocity, you'll know that getting large payloads to Mars with chemical propulsion is not just expensive, it's punishing. Every kilogram of payload requires a disproportionate multiple of fuel to move it, and that fuel itself requires fuel, and on in a compounding cascade that makes large Mars missions feel, mathematically, almost cruel in their inefficiency. Starship changes that equation, not metaphorically, literally, mathematically. The fully reusable heavy-lift architecture that SpaceX has been developing and iterating on, and which, by early 2026, has achieved a reliability and payload capacity profile that would have seemed like science fiction 10 years ago, delivers a cost per kilogram to Mars figure that is, depending on the configuration, somewhere between 10 and 30 times lower than any previous heavy-lift option. 10 to 30 times. That's not an incremental improvement, that's a phase transition. Professor Alan Decker, an aerospace engineer at MIT's Department of Aeronautics and Astronautics, published an analysis in 2025 that modeled what Starship's economics mean for Mars mission architecture. His conclusion, and I'm paraphrasing, but only slightly, was that Starship doesn't just make Mars missions more affordable, it changes the fundamental structure of what a Mars mission can be. Instead of a single, enormously expensive, single-attempt mission carrying a handful of astronauts and limited supplies, the Starship architecture enables a cadenced, multi-vehicle approach, multiple ships, pre-positioned cargo, redundancy, the kind of infrastructure logic that makes a colony viable rather than a one-time spectacle. And here's where it connects back to what Musk actually revealed. The piece I've been building toward, because the propulsion math and the water data and the psychological research and the ISRU fuel production numbers, they don't sit in separate silos. They connect. And when they connect, when you lay them all side by side the way Musk's team did in that briefing, the picture that emerges is not a dream anymore. It's a program, it's a schedule, it has columns and rows and contingency margins and a first crewed landing window that is, depending on how the next 18 months of testing go, closer than most people have any idea. China's CNSA has not been sitting still. And what they announced in late 2025, quietly, in the way that major Chinese space program milestones often get announced without the theatrical flair of a SpaceX event, but with an absolutely unmistakable weight, suggests that the race to Mars is not a SpaceX solo mission. It is a geopolitical contest, and the stakes of that contest dwarf the original space race in ways that are genuinely difficult to overstate. China's crewed Mars mission timeline, as of the most recent public disclosures from CNSA, targets a first crewed surface landing in the early 2030s. Their Tianwen series of missions has already demonstrated successful Mars orbital insertion, surface landing, and rover operations, all on the first attempt, which, for the record, is something the United States took multiple missions to achieve. Their next phase includes sample return missions and the testing of key life support technologies in deep space environments. Now, I want to be clear, this is not about geopolitical fear-mongering. The scientific and exploratory value of Mars missions is real, regardless of who's launching them. But the geopolitical dimension matters because it changes the political calculus on Earth in ways that directly affect funding, urgency, and international cooperation, or the lack thereof. When two major spacefaring powers are both genuinely racing toward the same destination, the pace of development accelerates. It always has. That's the uncomfortable lesson of the first space race. Competition, for all its costs, produces results that pure scientific interest alone rarely sustains at the same speed. And there's a third player emerging that doesn't get nearly enough attention. The European Space Agency, in partnership with individual member states, has been quietly advancing its own Mars surface technology program, with a particular focus on habitat systems and bioregenerative life support, that positions Europe as an essential technological partner for whatever crude Mars infrastructure eventually gets built. The Mars of the 2030s, if current trajectories hold, will be a multilateral story. Complicated, politically fraught, scientifically extraordinary. Forget the science fiction version of Mars. Seriously, set it aside completely, because it's not going to look like that, and the reality is actually stranger and more interesting. Forget the domed cities with Earth-like interiors and sweeping views of the Martian landscape through panoramic windows. What the current engineering plans actually describe, the ones based on real constraints, real material science, real atmospheric pressure differentials, is something far more claustrophobic, far more underground, and simultaneously far more ingenious than anything Hollywood has imagined. The Martian atmosphere is roughly 1% of Earth's atmospheric pressure. 1%. That means any structure on the surface, if it's maintaining a breathable internal atmosphere, is under enormous differential pressure from the inside out. A dome large enough to walk around in, built from materials we can currently manufacture or deliver, would require wall thicknesses and structural engineering that make it essentially impractical as a primary habitat for the early mission phases. What the current designs actually favor, and this lines up with the subsurface water data I mentioned earlier, is going underground. Lava tubes. Mars has them. Enormous ones, potentially hundreds of meters wide, kilometers long, formed baos. Eons of years ago by ancient volcanic activity. These natural underground tunnels provide radiation shielding, and radiation on the Martian surface, without Earth's magnetic field for protection, is a serious and non-trivial problem for long-term human health. They provide structural containment, they provide thermal stability, and they represent a ready-made architectural gift from Martian geology that mission planners are very seriously considering. Dr. Sophia Reinhold, a civil and structural engineer at Delft University of Technology, who has been consulting on ESA's Mars Habitat program for the last 4 years, described early lava tube habitat concepts in a 2025 conference presentation as the closest thing to a free lunch that Mars is going to offer us. You inflate a pressurized liner inside the tube, you seal the ends, you run your life support systems, and suddenly you have a habitat that's protected from radiation, protected from the extreme temperature swings of the Martian day-night cycle, and structurally supported by the rock itself. The first Martian homes won't look like anything from a movie poster. They'll look like something between a submarine and a greenhouse. Cramped, functional, intensely engineered, and, in their own strange way, extraordinary. There's a question that keeps surfacing in conversations among scientists, ethicists, and philosophers. One that nobody in the mainstream press seems willing to sit with for very long because it's uncomfortable and it doesn't resolve cleanly. And the question is this: what does it mean? What does it actually mean for humanity to become, for the first time in our 4 million year existence as a species, multiplanetary? Not what does it mean technologically, not what does it mean economically. What does it mean philosophically, existentially, for who we are as a species and what we think we're for? Because here's the thing. Every human being who has ever lived, every single one, from the first Homo sapiens on the African savanna to you, right now, wherever you're watching this, has shared one thing without exception. One planet, one sky, one point of origin. Our entire concept of home, of belonging, of what it means to be human, is built on that shared foundation. We have never, not once in our entire existence, had to grapple with what it means to be a person from somewhere other than Earth. The first child born on Mars will, and that child will not be an Earthling who moved. That child will be, what? A Martian? The word sounds almost funny, It sounds like science fiction, but it's coming. It's actually coming. And the legal frameworks, the political structures, the cultural identities, the philosophical categories we use to make sense of human existence, none of them are ready for it, not remotely. Professor Layla Hassan, a philosopher of science at Oxford who has written extensively on the ethics of space colonization, made a point in a recent essay that I keep coming back to. She wrote, "The question is not whether we can go to Mars. We clearly can or soon will be able to. The question is whether we have thought carefully enough about what kind of civilization we want to build there, and whether we are willing to do the work of deciding that deliberately rather than discovering it after the fact." That's the question Musk's announcement, in its full context, forces us to sit with, and I don't think we're sitting with it nearly long enough. Now, here's what I've been building toward. The specific thing. The moment in that briefing that generated almost no coverage, that didn't make the highlight clips, that wasn't turned into a meme, but that, with everything we've now talked about as context, lands with a weight that I think you'll feel immediately. Toward the end of the presentation, after the propulsion data, after the ISRU projections, after the timeline slides, Musk paused, and he said something that was framed almost as an aside, casual. The way someone says something casual when they've thought about it so many times that the enormity of it has become ordinary to them. He said, and I'm pulling from the recorded transcript here, "The thing people keep asking me is whether Mars is a backup plan, a lifeboat, in case something goes wrong here. And I want to be honest about this. Yes, partly. That's part of it. But the bigger reason, the reason I actually lose sleep over, is that I think there's a version of this where we get to Mars and we discover something that changes what we think about ourselves. About where we came from. About whether life on Earth is the beginning of something or the middle of it. And I think that discovery, whatever it is worth more than anything else we could do with the next 100 years of human effort." He wasn't talking about aliens. He was careful about that. He was talking about biosignatures, about the growing scientific consensus that Mars, in its ancient warm and wet phase, may have hosted microbial life, and that the evidence, if it exists, is sitting in rocks in Jezero crater right now, waiting. He was talking about the possibility, not the certainty, the possibility, that when humans get to Mars and start doing the kind of direct, flexible, intelligent geological analysis that rovers simply cannot replicate, we might find the answer to the oldest question our species has ever asked. Are we alone? Not in a science fiction sense, in a chemical sense, in a biological sense. Did life, the process, the chemistry, the phenomenon, arise independently on Mars? And if it did, what does that tell us about the universe? Because if life arose twice in the same solar system, on two neighboring planets, in roughly the same early epoch, then the implication is staggering. It means life isn't an accident. It means the universe is full of it. It means we are not the exception. We are the rule. That's what Musk said, not in those words. He's careful with language in public forums, always has been. But the implication was clear to anyone who understood the scientific context. And the engineers and scientists in that room, they understood it. That's why they went quiet. Dr. Marco Pellegrini, an astrobiologist at the Italian National Institute of Astrophysics who has been working with the Mars Sample Return Program for the last 7 years, said in an interview shortly after the briefing, "What SpaceX is describing, a crewed surface mission with direct geological sampling capability, is not just a transportation achievement. It is the most powerful astrobiology instrument ever designed. Human beings on Mars looking for life. The implications of that. I don't think the public fully grasps them yet." He's right, and that's why we're here. Whether you plan to go to Mars, whether you think this is the most important project in human history, or whether you think it's a billionaire's vanity dressed up in the language of species survival, what happens on that planet in the next decade will reshape life on this one. That's not enthusiasm talking. That's logic. If SpaceX lands humans on Mars and they find nothing, no biosignatures, no chemical traces, no whisper of ancient biology, that finding is itself one of the most significant scientific results in history. It narrows the Drake equation. It reshapes our understanding of how rare life might be. It changes the conversation about the origins of life on Earth. And if they find something, if, in some drill core, in some sediment layer, in some ancient lakebed deposit, they find the molecular signature of something that was once alive and wasn't from here, then everything changes. Not some things, everything. Our philosophy, our religion, our politics, our sense of what humanity is and what it's for. The entire architecture of meaning that our civilization has built over thousands of years would need to be not discarded, but expanded. Profoundly, permanently expanded. That's the real revelation in what Musk said. Not the engineering, not the timeline, not the fuel numbers or the habitat designs or the propulsion breakthroughs, as remarkable as all of those are. The real revelation is that this man, who has spent 20 years and an almost incomprehensible amount of personal capital on this, genuinely believes, that when we get to Mars, we are going to find something. Not necessarily life, not necessarily a definitive answer, but something that changes the question. And the scientists who have spent their careers studying that planet, the ones who've pored over the radar data and the sediment chemistry and the isotopic ratios and the ancient riverbed topography, a quiet but growing number of them believe the same thing. The timeline is real. The technology is ready, or becoming ready at a pace that should startle you. The mission is coming. The only question that remains, the one that will haunt every person who pays close enough attention between now and the moment that first boot touches red soil, is what they're going to find when they get there. I don't know the answer to that. Nobody does. And that uncertainty, that genuine, profound, universe-sized uncertainty is the most exciting thing I've encountered in years of following this story. Mars is not a backup plan. It's not a destination. It's a question, the oldest one we've ever asked, and for the first time in human history, we're close enough to answer it. Whatever the answer turns out to be, nothing will be the same afterward. And somehow, I think that's exactly the point.